All right, so you might be sitting there wondering why are there so many triangles? Today we're going to be talking about the Pythagorean Theorem, which is all about triangles. Specifically, it is all about right triangles. It's a rule that works only for right triangles. It doesn't apply to other triangles, but it is a rule that's universal among right triangles. So what we're going to do, this is kind of one of the proofs of the Pythagorean Theorem, and I'm going to start with this little one down here. What I'm going to do is, first off, we know that this side right here is 1, and this side is 1. So each of our sides are 1 and 1. And then what I'm going to do is I'm going to actually go ahead and draw a square. Let's see if it'll let me draw a square off of each of these sides. Now, the area of each of these squares is also 1 because it's 1 by 1 square. Now, what I'm going to do is I'm going to go ahead and I'm going to draw a square off of this side as well. And what you're going to notice is, first off, we're going to figure out the area of this square. And if we look, we have 1 half, 2 halves, 3 halves, 4 halves. 4 halves means that we basically have an area of 2. Now, what I want to be really clear about here, and this is something that comes up, is if we have a line that goes like this, and we have a line that goes like that, these two lines are not the same length. We can kind of look at that and tell. We know that this going up and down, we can count right here is 1, 2, 3, 4. But if we're going diagonally through these, it's actually longer diagonally than it is straight up and down. Now, it's not 7 because we don't have to go all the way down and then over, but it is going to be more than 4 and more than 3 because we're cutting across that. But it's still got it's going to be less than 4 plus 3. It's going to be less than 7. So anytime we're dealing with a diagonal line, we have to be aware that this is going to be longer, right, than either of these two other sides. So we're going to come back over here and take a look at what we just did. We just said, hey, this right here, this has an area of 2. I'll draw the 2 in there. Maybe that'll work. And so we want to know, well, how long is that side? So how long is the side of the triangle there? Well, if this is a square, and a square has an area of 2, our formula for squares is side squared equals area, right? The area is the side length times itself. So in this case, what we have is we have an area of 2, okay? We have an area of 2. So our side length is going to be sides squared equals 2. Now, how do we figure out what squared equals 2? Well, that's really simple. We get the square root of 2. So, in this case, what we're going to see is that side length right there is the square root of 2. And that is how big that side is going to be. And we're going to go through and we're going to take a look at this, and we're going to draw a square right here. And we're going to draw a square right here. These squares are each 4. They're a little easier to draw when they're a bit bigger. Now I'm going to draw the same thing over here. Now this one's going to be, we're going to have to be careful about counting it. We've got, and the way that I like to count these is, I like to count all the whole squares first, which is these 4 in the middle right here, right? I've got those 4. And then if I look out here, this is another 1, 1, 1, and 1, meaning that this whole thing right here is 8. So what do we have? We have 4, 4, and 8. How long is that little side right there going to be? Well, if the square is 8, our side length here is going to be the square root of 8. Okay. Now you might be starting to kind of see the pattern that we're establishing here. I'm going to do another one. 1, 2, 3, 1, 2, 3, 1, 2, 3. How big is this? This is 9. 1, 2, 3, 1, 2, 3, 1, 2, 3. How big is that? That's 9. So how big do you expect this square to be when we go ahead and count it up. Think about that. Over here, we have a side length of 1. This square is 1. This square is 1, and our total is 2. Over here, this one is 4, and this one is 4, and our total here is 8. So this is 9, and this is 9. We can estimate, hey, we assume, hey, following this pattern, is it going to be 18? Is it going to be 9 plus 9? And if we actually go ahead and look at it and count, again, we can kind of use a similar method of counting all the whole squares that we have, like that. And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 in there. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 halves, right? And half of 12 is 6. So we get 12 plus 6, and that gives us 18. So what does this mean? Well, what this means that if you have a right triangle, right, any right triangle, and you take the area of the squares of the two sides, these two right here, the area of the squares of the two sides, then it will equal the area of the square of the longer side, which, by the way, the longer side has a nice funny name. It is called a hypotenuse. Nice Greek name to go along with Pythagorean. So the square of any two, the square of the two legs, these are called legs, hypotenuse versus legs. The square of the legs of a right triangle is equivalent to the square of the hypotenuse. So let's go ahead and use this and come up with another quick picture here. I'm going to draw out one of the most typical right triangles you're going to see. So, and we're going to do this. Now, you might have noticed both the last one where isosceles right triangles, where it was the same size. Let's go ahead and draw this out right here. And we're going to run 3 over and up. And then this one is 4 over and up. And then we're going to draw this. Now, drawing these triangles is a little tougher, or these squares is a little tougher, because you need to kind of follow a pattern that goes around in order to make a square. And so what I'm actually doing to draw this square, you'll notice, is I'm kind of going to draw the triangle right there on its side, and then I'm going to go 1, 2, 3, 4, 1, 2, 3, and that's going to be my next point. And I can kind of do that to make the triangle kind of all fit and go in correctly. So we come back here. How big is this? This is 3 by 3, so this is 9. This is 4 by 4, this is 16. Well, we can use our rule here to figure out how big this is. We have 9 plus 16 equals, and this is going to equal 25. And so this is 25. Now, the way that we turn this into a mathematical formula is we take our right triangle of indeterminate size, right? Right triangle, again, only works on right triangles. We call this A. This side right here is A. This side is B. This side is C. And we can write this rule out as A, that looks like a 9. That's not going to work at all. A squared being the square we make off of the side A, plus B squared being the square we make off of the side C, off the side B, equals the square of C. And so we can essentially use this with any kind of triangle to determine, hey, is this working? Is this a right triangle? We can use it to go, hey, we only know 2 sides of this right triangle. How can we go ahead and figure it out? So that's kind of the overall proof of the Pythagorean theorem, to give you an idea of how the Pythagorean theorem and why the Pythagorean theorem works. So we can use this if we have, for example, a triangle. And I'm actually going to do something here. I'm going to say that this is 5 and this is 12, and I'm going to ask you what that is. So now we've got an unknown. We know this is a right triangle. Well, we can use the Pythagorean theorem, 5 squared plus 12 squared equals x squared. So in this case, 5 squared is 25, 12 squared is 144, and that is going to equal x squared. X squared is going to equal 169. So we can figure out what x is by getting the square root. We can say, hey, the square root of 169 equals, well, it should be a 9, equals the square root of x squared, which really just gets us to 13 is x. So this is going to equal 13. Now we can also run into this kind of problem in a different way. We can run into it where maybe we don't know the one of the legs. We know the hypotenuse, but not one of the legs. So let me draw out 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. And what I'm going to do is I'm going to say, hey, this right here is 10. This is 8. What's this? And this is a right triangle. And so we can do this, or here's our unknown, right? So we can go back and we can use the Pythagorean theorem, but we have to be careful because we don't know x, right? X is our unknown. But x is not the long side. The long side is the hypotenuse, which is always c. So this is c. And then which one is a and b matter less? I usually put b on the bottom just so I don't confuse it with base. So it represents the base as well. So in this case, x squared plus 8 squared equals 10 squared. Okay, and if we can look at that, we're going to see that this is x squared plus 64 equals 100. And we kind of follow our basic algebra. In this case, we take away 64 from each side. Take away 64 from each side. We are left with x squared equals 36. And you're looking at this and you're going, okay, what squared equals 36? Well, in this case, square root of this, square root of that, and x is going to equal 6. And we can actually tell, kind of coming along right here, we can see 1, 2, 3, 4, 5, 6, that that's actually a true case where that is what we would see. X does equal 6. So in this case, x, which is b, equals 6, which is great because 6 and b look a lot alike, and it's hard to tell them apart, especially with my terrible handwriting. So that's how the Pythagorean theorem can be worked, kind of how it's used, and a bunch of cases there for it. We're going to be doing a few other things with the Pythagorean theorem, but this is kind of the intro to kind of why and how it works.